So we have another Catriona puzzle here where we see one big rectangle, and in it there are rectangles of different colors. And every colored rectangle, they are all similar to each other. And the question is, what fraction of this design is red? So before I start a geometry problem, I usually ask myself, do I have the right to call something some side of 1? And one way to check it is, would this problem change if I doubled every side? That's the same as, would this problem change if I change the sizes, but up to similarity? And if a side length is given or an area is given, the answer is no. But here, what we have to find is an area divided by the total area. That should be preserved under similarity. And so if you don't change the problem by, say, doubling every side, that means, yeah, you can shrink or enlarge this until one of the sides become 1. And that means instead of 2 variables, we can deal with 1. So this is an example where we can actually call something 1. And so in order to avoid fractions, I went, okay, let me call this smallest thing 1. So then this is 1 and this is 1. And then the other variable, well, the only variable, the other side would be x. So this little rectangle here is of sides 1 and x. And then if you move on, this next rectangle is similar to the previous one, but because of this arrangement, you see they have a side in common. Well, rectangles have 2 side lengths, right? And so you have 2 similar rectangles. They're either identical, or in the second bigger rectangle, the shorter side is what in the smaller rectangle is playing the role of the longer side, right? So we can say, for just a split second, I'm going to call this here y. The vertical side is x, right? So in this rectangle, x is the shorter side. In the cute little original smallest rectangle, x is the longer side. So just for a split second, I'm going to call this y, and let's say the longer side divided by the shorter. I go for longer over shorter because then this is going to be x over 1, which is one of the easiest way. And then in the other one, x over 1, and the same ratio in the other rectangle is going to be y over x. And then we solve for y, we get that y is x squared. And then you can sort of figure out, like, yeah, instead of thinking of a magnifying factor, we can think that the longer side is always x times the shorter side, right? And so that means that if in the second smallest rectangle, if the shorter side is x, then that longer side y turned out to be x squared. Now, this other rectangle has to be identical or congruent with the second one because their shorter sides are equally long, x long. So this is x squared again, and the same thing here, x squared. And there is one little lesson here, is that if you know 2 geometric objects, that they are similar, and then you match one corresponding side to be the same length, that's congruency. So you can just say, well, they're similar, so you can zoom in and out on one, and then you prove that their shortest sides are the same, then the whole thing, they're congruent to each other. Okay, and so we have 1x squared, 1x squared, 1x squared x. And then we can move on to this rectangle here. And again, the longer side is x times the shorter side. So this is going to be x cubed. But if you don't believe, let's call this side z for a second. Z over x squared is the longer side over the shorter side is the same as x over 1. And when we solve for z, we get z equals x cubed. And if this is x cubed, And again, in this biggest rectangle here, x cubed plays the shorter side, while in the previous one, x cubed played the longer side. So this is just going to be x to the fourth. All right, so we sort of chased around and we labeled everything in terms of x. So we just needed one variable as opposed to a and b. For x and y, we just have x because we said, let's zoom in until one of the sides becomes 1. And so now, so there are two options here. Option 1, we could solve for x. If we could solve for x, we could find the area that's orange here, but red in the original, and the total area, and then we could divide. That's option 1. Actually, that's what I did. But it could also be that we do not need to find the value of x. Maybe it's a fraction we can get because all the unknown terms would cancel out. Didn't occur to me that that's a possibility at that point, but I'm intrigued. I actually computed x. So let's see if we can just shortcut that and see what that ratio is. So the ratio that they want is the area that's red divided by the total area. All right. So let's see the red area. We have 3 little rectangles. That's 3 times x times 1, or 3x. And we have one more that's x squared times x cubed, which is x to the 5th power. So it's 3x plus x to the 5th power. We could factor out x, and then we get 3 plus x to the 4th power. But that's it. That's how far we can take this. And then the total area. We can do it piece by piece, but we can just go, the shorter side is x plus x cubed, and the longer side is x squared plus x to the 4th. So it's x plus x cubed times x squared plus x to the 4th. I don't know if it helps, but it is often the case that when we notice something, that is in our benefit. So these are very similar. Actually, they're almost, let's just factor out what we can. From the first one, we can factor out x, and then we get 1 plus x squared. And from the second piece, we can factor out x squared, and we also get 1 plus x squared. So what we have is x cubed times 1 plus x squared. Oh, squared. 1 plus x squared squared, right? And that's x cubed times x to the 4th plus 2x squared plus 1. So the ratio right now would be x times x to the 4th plus 3 divided by x cubed times 1 plus x squared squared. And I don't see any cancellation here. So it looks like we're not going to get the answer unless we figure out x. But luckily, x is pretty easy to figure out. So, well, that was some cancellation. We can cancel out x, but that's it. So we're going to have x to the 4th plus 3 divided by x squared times x squared plus 1 to the 2nd power. Okay. So maybe we should figure out what x is then, right? It's good that we have just one unknown. Instead of a and b, we have 1 and x, or x, because that means we just have to squeeze out one equation from the situation, hoping for the best. So what we have here is x cubed. See, these are the same, but I think we will get an equation if we just say, or we can say something simpler than what we could say something like 1 plus x squared plus 1 plus x squared plus 1 equals to x to the 4th, right? Or we can say 1 plus x squared plus 1 plus x squared plus 1 plus x squared equals to x to the 4th plus x squared. But yeah. So I think I think the easiest equation would be expressing that this line is 1 plus x squared plus 1 plus x squared plus 1, but it is also just x to the fourth. That will give us an equation in x, although it's a little bit scary because it seems to be degree 4. So the equation will be 1 plus x squared plus 1 plus x squared plus 1, 1 x squared 1, equals to x to the fourth. This might be a little scary at first because this equation is of degree 4. But if we clean up things, we get 0 equals x to the fourth minus 2x squared minus 3. So yes, this is degree 4, but it's a special case of degree 4 that we can solve, because if you notice, x and x cubed are missing. This is what we refer to as quadratic in x squared. So that means that with or without the introduction of a new variable, this is really a quadratic equation. If we say let a be x squared, then this equation will become 0 equals, well, x to the fourth is x squared squared. So that's a squared minus 2a minus 3. We can easily solve this for a, and then once we're done, we're going to solve for x from there. At first, you probably need this introduction of new variable, but eventually you're just going to go, well, this equation is 0 equals x squared squared minus 2x squared plus 3. And you will be able to sort of look at x squared as the variable for which to solve here. We always have the quadratic formula, but before we use that heavy machinery of the quadratic formula, it might be worth to just check out for, just spend a few seconds to see maybe this is an easily factorable expression. And this one is, because a squared, we can only get it from a. And then 1 and 3 is the only way we get 3 as a product. And then if we play with the signs, this here says, well, in front of 1 and 3, one of them needs to get a plus, the other one needs to get a minus. And this is telling me that the bigger one should wear the negative sign, right? Because now when we multiply back, we get a squared minus 3 plus a. That's that negative 2a minus 3. So a equals to negative 1 or a equals to 3. Here is the problem with introducing a new variable. You might say, oh, we're done, 3. But we didn't solve for x. We solved for a. So we have two equations, x squared equals negative 1 or x squared equals 3. This is not going to yield any solution among the real numbers. No real number will square to negative 1, but there are two of them that squares to 3, square root of 3 and its opposite. And then very quickly, the negative one is not gonna be possible because we're looking for a distance. So we have a unique solution for x. That's pretty good for a degree 4 equation. And so we go back to the fraction that we're trying to find. And that was x to the fourth plus 3 divided by x squared times x squared plus 1 squared. What's that? So, well, if x is square root of 3, then x squared is 3 and x to the fourth is 9. That helps. So then the fraction that we're dealing with is 9 plus 3 divided by 3 times 3 plus 1 squared. X squared is 3. 3 plus 1 squared. So we have 12 divided by 3 times 4 squared is 16. So we can cancel out the 3. And then we have 4 over 16 or 1 over 4. That's the kind of numbers that you get from the puzzles of Catriona Shearer. They are always beautiful, simple answers. So basically, this shaded in the original problem red area is 1/4 of the total area. So that's how you do it. Any questions? Thank you for watching.